Welcome back. We will continue discussing about atomic force microscope. We just got introduced to the concept of an AFM in the last couple of lectures. So, today we will do a quick recap of the major hardware components which we have already talked about, and then we will move on to the basic working principle of an AFM. Of course, atomic force microscope, one needs to understand, as I have already pointed out, it is a relatively new instrument. So, there is lot of development that is still coming up in this area. People are using it for various other things other than just routinely scanning the or acquiring the information about the surface topography. We will try to cover or give you a glimpse of some of these methods or advanced techniques also, but fundamentally we will discuss the basic operating principle in the two most widely used modes, that is the contact mode and the intermittent contact mode, which I have already talked. So, let us get started. So, this is if you look at this particular figure towards the right side of the screen, probably it makes much more sense to you right now. You understand that there is a piezoelectric element to which is the scanner essentially. We will discuss a little bit more on the scanner today. You understand this sharp cantilever tip, what is its or the sharp cantilever, what exactly is its role. You also understand that there is a sharp tip which is used for actually probing the surface, and then, so this is the tip. Then you also understand that there is a photodetector which is used to track the deflection of the cantilever. You also understand that there is a laser source which reflects back from the back side of the cantilever through the shining area it has. You know that there is a feedback control loop which maintains the constant deflection and things like that. So, here is a little enlarged view of the photodetector or the QPD or the position sensitive photodetector. So, essentially you now know that the laser beam bounces off the back of the cantilever onto the position sensitive photodetector, bounces of the back side. So, that is the reason this technique is known as the beam bounce method for the detection of the deflection of the cantilever, detecting the of the cantilever. This is sort of the industry standard. Every commercial instrument sort of uses this approach. So, we are not going to discuss any other methodology. As the cantilever bends, the position of the laser beam on the detector shifts. So, suppose you have a specific location of the cantilever corresponding to which, let us say, so you have this laser source out here. We will discuss about all these things in detail. So, let us say for this particular configuration, this is the spot where the laser beam is falling. Now, the moment the deflection changes, let us say now it sort of changes to this location. Okay. So, the moment it changes, what happens is the laser spot now shifts to some other location. Let us say this. So, this corresponds to 2, this corresponds to 1. So, there is now an error that is generated in terms of voltage between these 2 points, and as we have told in the previous couple of classes, that this error is now fed to the feedback control loop, which again sort of adjusts the position of the scanner in such a way, or the cantilever in such a way, by sort of elongation or contraction. Let us put it in generic terms as dimensional change of the piezoelectric scanner, so that the deflection of the cantilever comes back to the same level, and the reflected beam again goes and falls at location 1. So, this particular aspect we will understand in greater detail. So, as the cantilever bends, the position of the laser beam on the detector shifts. The PSPD itself can measure displacement of light as small as around 10 angstrom. So, therefore, this gives unprecedented lateral resolution down to about a nanometer, and if, down to about 10 nanometers lateral resolution is pretty routine without ultra high vacuum or anything, and a vertical resolution of a few nanometer is also achievable with an atomic force microscope. So, these things we talked about. We had also talked about the sequence of alignment. So, these are the hardware elements you have. You have the cantilever and the probe sitting over here, which has this reflecting surface, which can be seen from this particular shining silver area. You have two sets of screws for movement in the x and y directions respectively. You have a laser source from which the laser is coming. You have the scanner, it can be z direction piezo or it is a piezoelectric scanner. We will see that it is no longer limited to a z direction piezo. So, somewhere this cantilever is attached to the scanner, and first thing what you need to do as a part of your approach sequence is as follows. So, first thing is you have to adjust these two screws, so that your cantilever now shifts and the reflecting coating sort of goes below the laser path. Okay. So, this is the first thing you do, this is the stage 1 of your alignment process. Once this happens, immediately what starts happening is that the laser beam now starts reflecting from this reflecting area. So, now the laser path is traveling in this direction. You now have the position sensitive photodiode, and what you need to do, you again have two sets of screws over here for let us say the x and y motion, and what you need to do, you need to turn them in such a fashion so that the photodiode now moves and shifts to a location, so that its center is now in a position to accept the reflected laser beam. So, essentially you shift it in this direction, so that this is the location. So, we have already talked that this is a perfectly aligned atomic force microscope now. You need to understand that the surface you want to scan is still far away. So, this is the surface you would like to sort of scan or investigate under the microscope. You perform the process of alignment far away from the surface. So, what it means? It means that there is no interaction between the cantilever tip and the surface at the stage of alignment. So, this is important to understand. So, the first thing, one of the first thing you get going is after mounting the cantilever or the probe onto your atomic force microscope, which has an cantilever holder, and this cantilever holder is typically attached to the piezo scanner, which we will soon understand. The first process you operationally what you would be doing is to align the instrument, and that is achieved by two steps. So, you have two sets of screws, one for the cantilever holder and one for the photodiode. So, first thing you do is you rotate these two screws for horizontal motion in x and y directions respectively, so that your reflecting surface of the on the back side of the probe comes in the laser path. The laser light starts reflecting, and then you bring in your photodiode in such a fashion, so that the reflected laser light falls at the center of the photodiode. So, reading is essentially 0 millivolt. Okay. So, this is a perfectly aligned atomic force microscope, and what you need to understand is the process of alignment is performed far away from the surface. So, still there is no interaction. Now, once the instrument has been aligned, you now know already that you will be using this tip, okay, to scan this surface. So, the next process, of course, you understand is going to be bringing this cantilever or the probe close to the surface, and these are very small things. So, we have already talked this length of this whole cantilever chip is few hundred micron, and this has a height of few tens of nanometer. So, you can do it manually. The immediate thing that is going to happen is that you are going to break the cantilever or the probe. So, this is also automated, and typically some slow speed stepper motors are used to achieve this or to bring the cantilever or the probe in close proximity to the surface. This is what is known as the, so tip is far away, few microns to a few millimeter from the sample surface, and the next set you need to do is to bring the aligned cantilever probe. So, stage 2 would be to aligned close to the surface to be scanned or investigated. Okay. So, this is how it looks like right at this moment. This is an aligned AFM. So, the surface sample surface is far away. What you do is this stepper motor takes care and gives a vertical movement to either the sample. You either bring in the sample close to the tip, or you bring in that whole assembly close to the sample. It works in either way, it is the same. So, it starts to move, and then two things are important here. What happens during the sequence of movement, and the second thing to understand or realize, or immediately the question that should come to your mind, okay, I am giving a vertical motion, but the question is, when do we stop? Okay. So, we will talk about this. So, two questions. Number one is, what happens during the vertical motion by the stepper motor, or let us put it like, what happens to the cantilever when during the vertical motion by the stepper motor, and question number 2 is, when does this motion stop? Okay. So, what do you expect to happen? Firstly, what is happening is that here is the aligned cantilever and the surface is far away. So, this is stage 1. Stage 2 is you bring it close, but still it is quite far away. And what is this quite far away? This R, since we are now talking about two surface, the surface of the probe and the sample surface. So, if this R is sort of beyond 100 nanometer, nothing happens. But next, when it is even closer, so let us say this separation distance now is less than 100 nanometer. So, what happens? If you remember your potential curve, which is also given here, now, so 1 and 2 you had no interaction, but beyond this, so you are now, so this is the generic nature of the potential curve, we already understand this. So, let us say 1 was somewhere over here, 2 was somewhere over here, but let us say 3 is here. So, what happens? Now, you no longer can say that there is no interaction between the tip and the sample surface, there is interaction. So, interaction, yes, and the nature of interaction is attractive. Okay. So, therefore, and do not forget this is a cantilever. So, this end it is sort of fixed with the mounting or the chip, but this end it is free. Okay. And then in the previous class we had talked in greater detail about the spring constant, the material or the stiffness of the spring or the cantilever you choose. And we had argued that we will always go in for a soft spring or a cantilever with a lower spring constant. So, what does it mean, and how low is low? Essentially, it is essentially it is in such a range that it deforms to these type of forces, these type of intersurface forces. So, you now have a cantilever which sort of responds to these attraction forces, and what is the likely consequence? Since this is hinged on one side, this end, so I will sort of draw a blown up picture. So, now this feels an attraction. So, this R, first thing to realize is somewhere over here, let us say. So, there is an active interaction and this is fixed at this end and this feels an attraction, and additionally the cantilever is soft enough to deform to these type of forces. So, what happens is the tip starts to bend like this because of the attraction it feels from the approaching surface. Simultaneously, your vertical motion due to the stepper motor is still progressing. So, on one side this bends because of the attraction, and on the other side you are still bringing in the cantilever in closer proximity to the surface. So, consequently what happens, after a while the cantilever sort of touches the sample surface and it touches. So, this was the original deflection free configuration of the cantilever. So, anyway, had there been no interaction force or the spring was stiff enough not to deform to these intersurface forces, even then since you are bringing in the because of the vertical movement of the stepper motor, since you are bringing in the cantilever close to the surface, anyway it would have touched. But let us say it would have touched at a separation distance of r0. Now, what happens? So, let us say we hypothetically consider a case where you have taken a very stiff spring which does not deform to the intersurface forces. You use the stepper motor to bring it in contact with that, and let us say the distance of some datum, let us say here would have been r0, okay, or rk, let us say. But what happens here, if you now look at this separation distance, let us say this separation distance is rm, this remains is found to be higher than rk. So, what does it mean? That it means that had there, so it means that the tip of the cantilever has come in contact with the surface sort of before it should have come into contact had there been no attraction. So, we will write it down quickly. The tip has come in contact with the surface ahead or before even before, or let us put it like this, substrate earlier than a case scenario where there would have been no deflection of the cantilever due to intersurface attraction. So, I hope this is clear to you. So, here we take a aligned cantilever, it is far away from the surface. So, no intersurface interaction. You start a vertical motion using a stepper motor. So, on the force curve, position 1 where you have aligned is few millimeter away or hundreds of microns away. So, there is absolutely no interaction. You start the vertical motion, you are still at a regime where there is no interaction. So, the separation distance, let us say, goes on reducing. So, this was let us say r1, here this is r2, r2 is less r2 is less than r1, but still if we mark this as RC, the critical separation distance below which the interaction starts, here R2 is still greater than RC. So, there is no interaction, but then as you bring in the cantilever closer and closer, what happens is the separation distance, let us say R3 over here, is now lower than RC. Therefore, what the additional thing that crops up is now there is an active interaction between the two surfaces, that is the tip and the surface or the sample surface. So, and we also understand the nature of this interaction is attractive. So, what happens, since you have taken a cantilever or a spring which is flexible enough, the stiffness is low enough to deform to these type of forces, and the cantilever is mounted or fixed on this particular end. So, what happens, the probe end of the cantilever deforms or feels the attraction and starts deforming in this fashion. And simultaneously you must realize that the stepper motor is still active. It is still moving in the vertical direction. So, this whole thing progressively comes closer to the surface, and eventually there is a point where the deflected probe tip, this deflection is originating because of this intersurface attraction. So, you can understand you are bringing it closer. So, also the level of attraction increases. So, the level of that increased level of attraction gets reflected in terms of increased level of deflection. This is important. So, from 3 to, let us say you have come to 4, which is even closer. So, from 3 to 4, what happens is R reduces. So, increased attraction, and this gets reflected in increased deflection of the cantilever. Okay. And finally, what happens is at some point the tip touches the sample surface, and this you now compare it with a scenario where suppose there was no attractive interaction, which is a difficult case to imagine, because van der Waals force, as we all know, is one of the most fundamental forms of force. But you can hypothetically think about not exactly hypothetical, this is a valid point. You can think about a cantilever which is very stiff, which does not deform to these forces. So, what will happen? This is one of the things we had been repeatedly talking in the previous class about the choice of the cantilever material. So, suppose you take a cantilever which does not deform, and then if you trigger this motion of the stepper motor, anyway that will come in contact with the surface. It is not that it will not come in contact. But what will happen, let us say the separation distance at which it comes in contact is something like this. But what you will find here, that since you have an active interaction and the cantilever now bends or deflects, this cantilever tip or the probe tip comes in contact with the surface ahead of this RK. So, this is what is known as jump to contact. And this so called jump is a manifestation of the intersurface attraction between the probe tip and the sample surface. Okay. So, this is what happens. Now, even now what you need to understand that the stepper motor has not yet stopped. So, now you are in a situation where jump to contact has been achieved, and the stepper motor is still sort of pushing it down. So, this is the force curve. It has already jumped to contact. So, we understand in the force curve what is the point of contact, this is the point of contact. So, the tip is already here, okay, but your stepper motor is still pushing it down. So, what will happen? Progressively the deflection will now reduce like this, and finally, if it still pushes, it will, the deflection will change to something like this. So, I would put it like this, this is the configuration, let us say jump to contact, you push it further, it is going to be like this. So, what is the difference? Let us say we mark this as 5, 6, 7, 8 and 9. So, let us try to identify the points on the force curve. This is the point 5. This you see is a scenario where there is no deflection, it is again straight. So, can you identify that point? Beyond 5, what you need to understand that the any push that is imparted by the stepper motor, you are now in the repulsive regime. So, before jump to contact, you were traversing the motion of the tip was following, or the interaction was following the 1-5 part of the curve. That is the attractive part of the curve. Now, once the jump to contact has been achieved and the stepper motor still pushes your tip downwards, what now you are actually traversing the 5-9 part of the curve. Okay. And interesting thing is, so as you sort of the point 6 will be somewhere over here. So, what is interesting to note that locally there is now a repulsion, because the tip is already in contact with the surface, but overall magnitude wise you are still in the attractive regime, and therefore, the deflection is something like this. So, from the standpoint of a deflection of the cantilever, probably we can now identify that any attractive interaction will lead to a deformation of the cantilever like this, and any repulsive interaction, because of the fact that now this side is sort of is no longer free to move. So, this is now confined by its contact with the surface. So, whatever change in deflection occurs, that will now occur at this end in the shape of the deflection of the cantilever. So, an attractive interaction will have a shape of the cantilever deforming like this, while a repulsive interaction will have shape of the cantilever like this. Of course, when there is no interaction, it will be like this, it will be straight. But in between, you see that I have drawn deliberately a case 7, where again the deflection resembles the deflection at 1, where there was no interaction. So, no interaction means there was no interaction. So, let us try to locate the point 7. This is the point 7, where again the cantilever apparently appears, the deflection of the cantilever apparently appears same as that of the 1, but there is a vast difference between the two. In position 1, there was no interaction between the surface and the cantilever tip. So, there was no attraction, there was no repulsion, but at position 7, what happens is the net deflection on the cantilever is again 0, but this is because of the fact that the attractive component of the repulsion now balances or matches exactly the repulsive component of the deflection. So, once it crosses the position 7, now what happens? Now, there is it is in the net repulsive regime. So, now the shape of the cantilever sort of changes like this. Okay, so, this is the sequence of approach, or the first question we posed as to what happens to the cantilever during the vertical motion by the stepper motor. So, this is how the deflection of the cantilever sort of gradually changes. So, if I add here, so there was no deflection, then it starts to sort of feel the attraction, it deforms in this way, then it goes to jump to contact, then further approach sort of gradually reduces the overall attractive interaction. Finally, it again crosses to this critical point at 7, and then there is a net repulsive interaction. So, this is the overall sequence that happens that the cantilever sort of undergoes during the sequence of approach. That is fine. So, if you now look to these cartoons over here, probably it will make sense. So, this position corresponds to our location 1 over here, what we have manually drawn, where there is no deflection. Then the subsequent figure number 2 is similar to the figure 2 over here, where the motion has started, but there is still no deflection because of the fact that your R2 is greater than the RC. So, you are still somewhere over here in the force curve. So, still no interaction. Then the figure 3, you now see that the cantilever has sort of deflected due to the positive attraction. So, we have talked about it, it is it corresponds to this configuration. But what you now see additionally on this cartoon is something we deliberately did not talk. I did not wanted you to sort of get confused and avoided talking it. So, what we need to now understand how this deflection sort of gets manifested on the photodiode. So, if you remember these configurations, one is a sort of deflection free configuration, and if you remember the sequence of alignment. So, let us say this is the configuration 1 corresponding to the cantilever, and this on the QPD or the PSD implies that your laser light is getting reflected, and so this is the laser source, it gets reflected and falls at the center of the QPD. So, let us now go on adding these configurations or conformations or the position of the laser light on the QPD. So, on 1 the light falls over here. Okay. We understand laser comes, it is still aligned. So, it falls over here. Maybe I will draw it in a neater fashion. So, 1 it falls over here, here is the sample surface. At 2 it is closer, but still there is no interaction, we have talked. So, on the QPD there is no change in the position of the laser light, it still falls at the center. So, I would say R1 is greater than smaller than RC, R2 is also smaller than RC. Then we come to location 3, where I am sorry, R1 is greater than RC, R2 is greater than RC, okay. But R3 is now less than RC, and what is RC we are talking about? RC is this critical location on the force curve we are talking about, below which there is active interaction, beyond which there is no interaction. Okay. So, R3 now is less than RC, and we already understand that because of the attractive interaction the cantilever now bends like this. And simultaneously what happens is, now since there is a deflection on the cantilever, so the laser light no longer falls on the center, but it sort of shifts, and this is exactly how a deflection is spotted. So, if you sort of compare with the fact that at perfectly aligned condition the deflection was 0, you already see that because of this deflection corresponding to the attractive force experienced by the tip due to the approaching surface, there is already a shift in the laser light. Now, so subsequent step would be, let us say the step 4 or step 5 would be jump to contact. Next step is jump to contact. Sorry, I just avoided the trouble of drawing it once again, and now it is in jump to contact. So, as we understand, we have already talked that as the separation distance sort of reduces, the attraction progressively increases. Okay. So, separation distance reduces, you are traversing in this direction because of the motion of the stepper motor. So, the attraction increases, and what does that mean? Attraction increases means that progressively this deforms more and more, and consequently from here, this was the location of the aligned one. As the attraction increases, the laser light sort of drifts more and more from the center. So, from let us say position P1 to P3, higher level of attraction. I hope it makes sense to you. Well, we just wrote it here. So, let us say from 3 to 4 we drew on this particular curve. So, just have your attention on this part of the view graph. We talked about 3 to 4, and let us say this is the point 5 we say. So, we also change it to P3 to P5. So, 3, 4 are both points. Let us try to understand what is 3 and 4. 3 and 4 are both points in the attractive regime. In the attractive regime, however, it is not in contact. Okay. In contrast, 5 is the point where the jump to contact has been achieved. Okay. So, from 3 to 4, so before it started to experience the attraction, let us say up to the point P2, the laser spot was falling still at the center of the QPD, there was no deflection. Beyond this point 2, it started to experience the attraction, and therefore, its configuration started to change from a deflection free configuration to a configuration which corresponds to an attraction, and consequently the laser spots also started to shift in this direction. So, here we wrote that from 3 to 4 or any point, R reduces, the separation distance reduces. You can see that the separation distance, the inter surface separation distance, the separation distance between the tip and the sample surface progressively reduces, and consequently the attraction increases, the attractive interaction increases, and this results in increased deflection of the cantilever. Okay. Up to this we wrote. What we did not write then and what we understand now, that this also leads to higher level of deviation of the laser spot on the PSPD from its central point. So, higher is the level of interaction or level of deflection on the cantilever, higher will be the extent by which the laser spot shifts from the center of the QPD or PSPD. So, I will just do a quick recap from. So, at very far away the AFM is fully aligned. Okay. So, the laser spot reflected, the beam, the bounced laser spot falls at the center, the stepper motor starts to move, still you are beyond RC, there is no interaction. So, the laser spot still remains at the center. Now, you come to a separation distance which is closer than RC. So, consequently, your cantilever now experiences an attraction. The moment it starts experiencing an attraction, what happens is the laser spot also shifts its position from the center or its aligned location, and then you by virtue of the motion of the stepper motor, you bring the tip even closer to the sample surface. Two things happens. First thing is the separation distance reduces, the magnitude of the attractive interaction increases. This increase in the magnitude of the attractive interaction gets reflected as an increased deflection of the cantilever. As we have documented it here, it results in an increased deflection of the cantilever, and this increased deflection of the cantilever results in progressive or gradual shift of the laser spot from its aligned central location. One can also understand the maximum distance or the maximum deviation will occur at the point it sort of comes in contact. Okay. We have drawn, please do not get confused that it has to move in this direction, but we have drawn it just to explain the things to you. It is a QPD, so it is similar to a graph paper. This is first quadrant, second, third and fourth. We argue that this is the attractive regime or the negative force. So, we are in the sort of negative side. It is nothing really hard and fast that it has to move in this direction. One can always argue it has moved in this direction due to the attraction or any direction. Only thing is you need to keep the force curve in your mind. So, now we understand that this is the this is the position of the laser spot on the QPD at jump to contact. Now, what happens beyond jump to contact? What happens beyond jump to contact is if you still go on pushing the cantilever, if the stepper motor still goes on pushing the cantilever, what now happens is now the deflection sort of starts reducing, because you are now following this part of the force curve. So, as the deflection starts reducing, what happens is now, so let me draw it again, an enlarged view. So, this is where the laser spot was at alignment. This is how it progressively shifted as the cantilever tip started experiencing attraction, and let us say this is the maximum deviation we see at jump to contact. Now, beyond jump to contact, if the approach process is still on, now the attraction or the deflection progressively starts reducing. So, consequently, as it starts reducing, so as the deflection was increasing in the attractive direction, it sort of shifted in this direction. Now, as the deflection reduces, the laser spot now goes back along this particular way, and all the way you must understand that at point 7 we again encounter a situation where the net deflection of the cantilever is 0, which is identical to the conformation of the cantilever after alignment, or in other words, now the laser that gets reflected again falls back on the center, and beyond point 7, if you push the cantilever further due to this approach, it is now in the repulsive regime. So, now for the first time the laser spot starts shifting in this direction. Okay. So, you need to understand that if this is the attractive regime, this is the now the repulsive regime, and the other thing that should remain in your mind, that the configuration of the cantilever or the nature of deflection of the cantilever in the attractive regime remains like this, the nature of deflection of the cantilever in the repulsive regime remains like this. So, this is again we get back to the two questions we posed at the beginning of the class. What happens to the cantilever during the vertical motion? So, now we understand the full cycle, what happens to the cantilever. From here down to 2, nothing happens. Beyond this, it experiences an attractive interaction. Beyond that, there is now repulsion, but that also can be split into 2 parts. So, first you have a repulsion, local repulsion at the tip, but the overall you are still in the attractive regime. So, you have a situation like this where locally there is a repulsion, but you are still in the attractive regime. therefore, your sort of deflection is still like this. Then you cross this critical point at 7, where the attractive interaction balances the repulsive interaction, and then you are in the completely repulsive regime. So, in addition to that, we now also understand how the laser spot progressively changes location on the QPD from here at let us say point 1 down to point 5 over here at approach, then again all the way back during this particular part, and beyond 7 it is like this. Okay. So, this is how the whole sequence of approach sort of leads to a deflection as well as the movement of the laser spot on the QPD. But if you look at the second question we had posed, we still do not have any clue about it. When does it stop? When does the motion stop? Because what is going to happen? It is now in the repulsive regime, and you still go on pushing it, or your stepper motor still goes on pushing it. Okay. So, finally, what is the likely consequence? Likely consequence is that if you do not stop, it will just snap off, the cantilever will simply break. Okay. So, what needs to be done, that you need to define a force at which the stepper motor should stop. Okay. And that force can be, let us say, 2 millivolt, 3 millivolt, whatever it is. But typically, remember that what we are going to discuss is contact mode AFM, but for other modes also, imaging is always done in the repulsive regime. Now, this is a gross statement, I would say. So, I will add for contact mode, which is the simplest one, and we are going to discuss it soon or shortly. Okay. So, now, so again we repeat from 1 due to the attraction is goes all the way up to 5, which corresponds to the jump in contact. Then beyond jump in contact, again it traverses back this path, crosses 0 again at 7. So, this point now corresponds to 1 as well as 7, and then now there is a net repulsive deflection, okay, and the moment sort of the deflection matches this set point. Okay. So, let us say 2 millivolt is here and your deflection is shifting like this. The moment it matches this 2 millivolt set point, the approach stops. So, in other words, what happens is, so let us say this is your set point you have specified. So, 2 millivolt you understand it, the moment this deflection now matches 2 millivolt, the approach stops or the stepper motor stops. So, stopping criteria of the approach sequence, the moment the deflection on the cantilever becomes equal to the set point, which is user defined. And this force at which you would like to scan is a function of whole lot of things: stickiness of the surface, stiffness of the surface, and to a large extent is a function of operator choice and operator experience. What happens when the deflection becomes equal to the set point, the approach stops. Now, stopping of approach concurrently activates the piezo scanner, and the feedback loop. So, the feedback loop essentially is a PI or PID controller depending on the situation, but important thing to remember is that the feedback loop will generate an error based on the set point. We will see it in the immediately preceding discussion. The feedback loop please do not confuse that the feedback loop generates the error from the center of the QPD. The feedback loop, I will write it down and keep this in your mind. Feedback loop does not generate error based on the center. Okay. So, this is how the whole thing looks like. So, let us revisit this whole cartoon again. So, set a set point, and so this is the align cantilever. You now trigger the stepper motor. So, it is moving now. First it comes closer, but nothing happens. So, you are still beyond that point of let us say RC, and so you are still beyond RC. And then you come closer. So, there is a net positive attraction. So, the cantilever deflects like this, and now you see if you examine carefully over here, which we did not do before, is that this is the center, it has deflected like this, and you see there is a small green spot. So, this green spot was here right from this particular figure. So, this green spot is nothing but the set point. Okay. And then what happens is you approach further, and finally, the nature of the deflection changes from attractive to repulsive, and when the reflected beam sort of goes and coincides on this green spot, that is the set point, now your approach sequence stops and the piezo gets activated, the feedback loop is activated, and the AFM is ready to scan. So, these also capture sort of the configuration of the nature of the deflection on the cantilever, as well as how the laser spot sort of moves on the QPD. So, this is at the aligned position, this is when it is subject to attraction, it shifts in this direction. This is beyond jump to contact, it is now traversing back following the same path, some of the figures we had drawn. So, after alignment it was over here, then due to attraction it sort of drifted in this direction. This corresponds to the jump in contact, the maximum deviation in the negative direction, and then since you now start traversing this part of the potential curve. So, it follows back the same path, and then finally, when it matches the set point, it stops. It is now ready to scan, which we will how the AFM scans in contact mode, we will discuss in the subsequent class. Important thing to note is an AFM imaging is always done in the repulsive regime in the contact mode, and why that it is the case we will discuss in the next class. Thank you.